It was 40, 40, 20.
Oh, really?
Yeah, because that was 100 points. So you would have done.
Oh, yeah. 40, 40, then 20. The first problem I got from credit. The middle problem really screwed up.
82. That means you got.
I got 22.
Yeah. I mean, when you had the 5 points, then that's still high.
Yeah.
And
I said
Dr. Rao, he has a flat 4% grade rate at the end of the semester, 2% if you do the riddle evaluation, and another 2% if you do his evaluation. So 86 and above is Peter was telling me. And homework is 20 on your grade. If you just do your homework well and consistently and get 85, 90 or above, that's essentially a midterm grade that you're getting 85 above or higher.
I can just hear you over the class.
Okay, good. Yeah, because class is so noisy. Anyway, Julian, can you hear me? Check, 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 check. Can you hear me? Hello, hello. Say something. Audio checking.
So you gonna remember this time, or am I gonna get to hear your rip again?
Thank God I remember.
Hello, hello.
So I finished the fly dot. I finished the second.
Okay, he's not responding, so I have to pick it up.
So I finished the analytics, but before I could go on it, I realized I had to go grab the entry competence class. So like as soon as I get out of here, I'm gonna go put them all into the one tab document and throw it into the group chat.
Yeah, so we fucked ours up.
What did you do?
Well,
Pictures video not live.
Okay, totally.
You just think you have that.
Say something.
Good. Rated is super complicated.
Okay, good. You're back. So 2 people right today. Peter's here. Good.
Oh, yes.
How was online experience? Could you? It was about the same. It was about the same quality, I hope.
Yeah.
Okay. It's more private, isn't it?
Yeah.
I guess it could be better. I don't know.
Stupid and trash because we just didn't want to really, you know.
My teammates just made they worked on the lab, and I just started looking at it and trying to figure out.
Yeah, one thing I'm wondering is
I'm like,
because I cannot broadcast with YSF. So this is Wi-Fi. So I was wondering about the quality because this is Wi-Fi.
Oh, it's
It was okay.
we started doing
audio
it.
is just fine.
Okay.
This is with me and my other team, and then Peter basically put the entire thing
Still have time.
and did all of the MATLAB. And then I took it and made it for the
Okay.
requirements, like, oh, put names on it, and write down the explanations for why these values are this, why your min is, you know, what it is, why your max is what it is.
That was a good thing it's still 11,
Yeah.
5. I just realized that today.
Yeah, no, that's a
good
godsend.
thing. Yeah, no, after
And
this,
Michael,
I'm gonna go die.
did you make a decision about the special project? Did you make a decision about the special project of X5?
And, oh, what's that? You have 2 hours to submit.
Yeah.
It's upside down. You have 2 hours to submit.
Exactly. It's basically we need to define it after you come to agreement that you're gonna do something special. Then we make a definition for what's special.
Yeah.
It's negotiable. It's scary, isn't it? But it's something like that. And he knows. I mean, Stephen. It's about something. Anyways. Oh, okay. So it's about time now. All right. So let's take a draft attendance. Okay. So yeah. And Zach. By the way, Stephen and Zoe are 19. Am I correct?
Yeah, correct.
Just checking. They're on.
The Eagle Nautics exclusive project, like what you're doing for RRD, the guys in Eagle Nautics have that.
Oh, you guys got it.
Yeah, Stephen and I are working together.
By the way, did Jen, I picked the notes. Okay.
The other 2 guys, Michael and Ian, didn't want to do it, but Stephen and I are working together. He's the guy who recruited all of us.
You can put in the computer lab? In the computer lab? Or is that where you're gonna work?
Most likely, because it requires a program called X55, which actually the final project for this class is in X55, so we're kind of and you're going to be using it in the club and for CAP stuff, so it's definitely something that's really helpful. So we're probably going to
I
have
should
the,
see you there sometime.
Oh, yeah.
Just very quickly about the correction of my Unit A3 notes.
That's most likely what we're doing.
Let's take a look. Okay,
A3A.
A3. Did you find out that there's a small issue in my lecture note that actually kind of makes sense. So, yeah, I actually appreciate your comment. So this is the isentropic flow and the isentropic relationship. It's basically the ratio between location 2 and 1, 2 and 1, 2 and 1. Now, as you move to next page, in old version of notes, okay, this was actually 1 over 2, 1 over 2, 1 over 2. So it was kind of confusing, so I fixed it.
Shouldn't they be the same equation?
I know, but
Okay.
it's misleading.
Okay.
Yeah, that's right.
Wait, same equation?
No, it's the same equation, but because it's based on your definition where it's 1 and where it's 2.
Yeah.
So it's going to generate the same thing, but
Oh, thank
since
God.
it's misleading because 1, 2, 1, 2, 1, 2,
Just to
1, 2,
clarify,
1, 2.
can you draw a streamline?
That's right. So that's all depends on how you draw a streamline. Where's your 1, where's your 2?
Just to clarify, can you draw a straight line for that one?
For that one.
That'd be kind of unfair.
This is a streamline.
Done.
This is 1 and 2.
One, that's two, okay.
Or you can say this is 2, this is 1. Then you can still apply the same equation.
Perfect.
But anyway,
It's almost as if it's a long history.
this is usually, you know, upstream is 1, downstream is 2. That's your sort of common sense kind of thing. So, but anyway, I want to avoid the misunderstanding, that's why. But I really appreciate your pointing out, because this was not consistent.
Yeah.
Yeah, so I try to make it consistent. Okay. So this is A3. It is the same equation, by the way. Okay, so now let's take a look at updates. No new updates. So hopefully you're working on quiz 5. Quiz 5 is due Monday noon. Quiz 5 is all about low speed wind tunnel if you use hydrostatic probe to determine airspeed. Obviously people talk about inches of water. And then what is it? And why do we need to use that? And then those kind of things. I want to hear your explanation. It's not that plug and check and get the value correct, and then I'm okay with it. No, I want to know if you really understand why you have to use inches of water, the reason, and then what is the benefit. And then suppose if you have a special device in low speed wind tunnel attached to the wind tunnel facility, gives you direct reading of inches of water, how can you design such a thing? What is the angle? What is the liquid inside? What is this much rings? It's going to be inches of water. How do you design such a thing? Because in the future, you may end up doing that. So that is something I'm interested in. Not that number is correct. So what kind of response? Okay. And then especially if you are aero track student, you're going to take what class? Experimental aerodynamics. I know who's going to teach it, but you're going to end up taking the class. And then please don't tell me, oh, what is into the water to that professor. He's going to blow up. Of course, he assumes that, oh, of course, you know it. Well, who the hell is AE301 teacher kind of thing, you know? I don't want to hear that kind of comment. Okay. So that means if you don't understand those basics, you're not going to pass this class. I force you to. Okay. So quiz 5, hopefully you're working on it. So this is more or less, this is a genetic device, something called differential inclined YouTube manometer. You can find this in wind tunnel lab. You just open up a cabinet, find one of those things. Then you're going to set it up using this device, of course. Airspeed measurement device, I know what it is, and you know what it is. And then you're going to combine those, and then this kind of device, and then reading off this inches. This may not be inches of water, but some kind of inches combined with angles, and then this is the length you get. Then what is the airspeed? So this is a little bit more generalized version of Quiz 0 Problem 5. Quiz 0 Problem 5 is a specially designed device for that particular wind tunnel. Right?
Is this quiz 5?
This is Quiz 5, yeah, you're looking at it. Haven't you looked at it?
No.
This is the Monday. It's been posted like when? Well, you know, it's been a while.
Like this Monday.
Go ahead.
For part A, do you
Part A.
in the description, do you want more theoretical descriptions, including the equations, or do you just want it in our own words?
You know, it's fine, as long as you convince me that you understand. You can use equation, or you can use your own words, just words only, or including equations. But one thing I don't want to see is just equation only. It just gives me an impression that, hey, this person just memorizes equation. I'm not sure if this person understands it or not. Your ability to explain something is quite important. That is the skill. That's sometimes people call, well, communication skill, strong communication skill. We desire. What the hell is that? Nobody knows. And people know those things. I can tell. Okay. If you're sitting the other side of the table and you cannot explain anything, that means, okay, that's it. Who's next? Kind of thing. Okay. So, any question about quiz 5? This is due Monday. I hope you figure it out before weekend. Okay. So today we're going to move on. Let's take a look at airspeed measurement. First of all, raw speed, because raw speed sets the standard process of calibrating weather.
Sorry, I didn't mean to interrupt you, but I had a question from last class. You were talking about how the pedostatic probe is basically, it's going to measure inches of water. So in like an airplane, right, they often, you know, tell pilots it's got like a certain stall speed.
That's fine.
Is that actually inches of water? So like
No, it's a
when
knots.
yeah, but when the exact like moment where it's not enough lift anymore, is that going to be based on inches of water?
Everything in terms of knots, actual speed. In other words, that's actually quite important thing. If you're talking about wind tunnel test speed, the meaning of using inches of water is that something you can basically guarantee. That is the capability of this wind tunnel. That's the inches of water. You can never know actual miles per hour. Like I said, in order to know that, you need to have one information which you can never directly measure, that is air density. So airplane need to do something for that. So today's subject is precisely that. So how on earth in airplane, actual airplane, figure out actual airspeed? And then actual airspeed, especially low speed to begin with, depends on the actual value of density of your flight altitude. So how can we get that kind of information? And then what is the device that the pilot has in the pocket to determine actual flight airspeed in knots? Knots is essentially actual speed. So we're going to talk about today lots of terminology that the airplane pilots use. First of all, KS, knots indicate airspeed. This is the pilot's terminology, knots indicate airspeed. This is what airplane tells the pilot that you're flying with this knot, which is actual speed. But obviously, a good airplane pilot, especially Embry-Riddle students, they don't trust it. They know that this is not the real airspeed. So somehow they have to find out knots in true airspeed, K-test. This is what they want. But the airplane is not capable to get that value up front. At least the airplane cannot indicate that kind of thing. So airplane pilot always need to do calibration. That's why flight computer comes into play. So we're going to talk about it today. That's actually a very good question. So inches of water applies only for wind tunnel testing because that is the capability of wind tunnel. If people ask you how fast this wind tunnel can go, the only answer you can give is inches of water because that's the capability of the wind tunnel to produce that much dynamic pressure head. Okay. So that is, you're talking about pressure. This is how much dynamic pressure I can produce out of this wind tunnel. And I don't really know actual airspeed in it because it depends on the air density, location, today's weather, season, and all that, temperature, other things. That is going to determine actual airspeed in the wind tunnel. Now, in case of airplane, you cannot say that. because you want to know actual airspeed I'm flying right now. So let's just take a look at it. Go ahead.
So when I was touring and the guide told me an actual speed, he was lying to me.
Unless it is KTAS. If the guy is, oh, I keep telling you KIAS. Oh, that's what I meant. That's actually very accurate.
That's what I
That
meant.
means, well, you know, because I'm just telling you that my airplane is telling me I'm flying 87 knots. That's, I'm telling you, that's KIAS, KIAS. And in order, oh, you wanted to have a KTAS? You didn't tell me that? Hey, pick it up. Pick it up, flight computer. Oh, I'm actually flying 97 knots. Okay, so anyways, so calibration process, let's just go over it today, this page, okay? So we started out from the airspeed equation for roll speed based on the Bernoulli equation. So this is the equation for oftentimes called KTAS, knots in true airspeed. This is the equation, knots in true airspeed. Now this is purely academic. The reason is, how can we tell actual air density when you're flying? It's impossible. So this information is always depending on some other things, such as pressure and temperature. Pressure and temperature you may be able to determine or sense as you fly, but never be this value. Okay? So airplane can only show you this. This is knots in equivalent airspeed, KETS. Okay? So this is knots in true airspeed, KTAS, KTAS. This is knots in equivalent airspeed. Those are not the same. Go ahead.
So that rho infinity you have is the density of air.
Actual flight altitude. Actual flight altitude.
What is the rho s?
Huh?
In the equivalent airspeed.
What's this? Good question. Anybody?
That's static.
This is the sea level standard value. Well, of course, everyone knows the standard sea level value of density of air. Yeah, standard sea level value of density of air. Everybody knows. So, because we never know this value, we purposely choose this value to come up with airspeed. That's called knots in equivalent airspeed. Equivalent airspeed. That means suppose if the air density is the value, which is standard sea level, this is your airplane's flight speed. It's today standard day. Are you flying at the sea level? Both know. So that means pilots know this is not true airspeed. That's called equivalent airspeed. Okay? So typically, let's begin with low speed and then we can apply in high speed. But let's go through this process. I to C to lowercase e to t. ICE-T process, typically called. Okay. If you start taking flight mechanics, this is called ICE-T process. Indicated to calibrated to equivalent to true. Those are the series of calibration process to get actual airspeed in your flight. Somebody was raising hand. Go ahead, Stephen.
So your equivalent airspeed is always going to be lower than your true airspeed.
Precisely, that's the point. That's why this is lowercase. Out of all of those airspeed, the different kind of definitions, this is the lowest value. That's correct. Because at the sea level standard, density is highest, right?
Yeah.
So that's why this is the lowest value. Go ahead, question.
So do we more use the equivalent airspeed?
Again, that's just the way. Let me go through it, okay? So let's just find out each one of those things. Go ahead.
Just double checking, P naught is the dynamic pressure and P infinity is the static pressure.
I guess so. Let's move on. So based on the airspeed equation, okay? That's Bernoulli, okay? I'm not gonna cover that.
No, I'm subscript.
Well, that's a true mechanics. I assume you already know that, okay? Please let me cover the arrow. All right. Anyway, so this is the equation coming from Bernoulli's equation, right? Of course. So obviously, this is the dynamic pressure, right? This is the only information you can get from the device. Dynamic pressure, pressure difference between center tube and side pole. So you can determine this And then in terms of inches of water, this could be 5 inches of water in low speed wind tunnel, of course. Okay? Now in flight, this is the only information your airplane can get out of that device. Now the question is, what kind of density you're going to choose to determine airspeed? And density is something that you can never directly measure. You have to depend on some other things, pressure and temperature. Typically pressure, you can sense it, right? Because the static boat senses the static pressure, which is atmospheric, if it's a real airplane. Okay? So P infinity is probably, you can get it. What else do you need to find rho?
Temperature.
Temperature, yes. That's called OAT. That's an important term. OAT. Outside air temperature. This is critically important information you need to determine true airspeed, obviously. Okay? So let's go through the ICT process here. So first of all, I and C and E, those are essentially nowadays, especially on an airplane, just about any airplane, this is all instrumentation automated process. In other words, you're going to establish your airplane's instrument, and then that instrument is connected to the pilostatic probe. That is going to sense the dynamic pressure. Then using this equation, then instrument indicate whatever the airspeed that instrument believes it is. Okay. That needs to be first of all calibrated. Location of the pilostatic tube, of course, it matters. The optimum location of pilostatic is, of course, the nose. Yeah, so that's why you see those experimental airplanes comes with nose-mounted pilostatic. But in practice, if you go for like a production of airplanes and manufacturing process, they often move it to some other places, right? Because nose needs to be used for some other things, like radars and other things. So you have to calibrate for that kind of errors. This is called calibrated airspeed. Usually small, tiny calibrations is in place, okay? So this is going to be I to C. So this is more accurate than just the indicated airspeed. The indicated airspeed from instrumentation always comes with errors. That error needs to be calibrated, first of all. Then that one is going to be bring it down to equivalent. That means you're going to calculate something called F factor. Something called F factor multiplication. Do you have a question, by the way, guys? What is it? Please don't hesitate. Okay, so F factor correction is involved. In other words, this is F factor table. If the calibrated airspeed is 200 knots, and then if your pressure altitude, what is pressure altitude? Anyways, pressure altitude is 10,000, you have to multiply 0.995 to the calibrated airspeed to come up with equivalent airspeed. This is called F factor correction. Okay. This is usually taking care of the standard altitude-wise. What is the density ratio between that altitude to the standard sea level? Okay. So this is automated process. Those are the values already included in your instrumentation. So from the pilot standpoint, your airplane is always showing you this equivalent. So a pilot oftentimes says, this is my airplane indicates to me. This is oftentimes called indicated airspeed from pilot's perspective. But we engineers do not use the term indicated airspeed. We use equivalent airspeed because we know that this is the airspeed which, if air density is standard sea level value, equivalently, this is the airspeed you should have. That's the meaning of equivalent airspeed. But pilots don't care. They take a look at airplanes indication saying, oh, this is what indicating airspeed. So that's the source of confusion comes in. I was so confused at the very beginning saying, well, pilot says indicated airspeed. We engineers talk about equivalent airspeed. Are those different? Actually, I realized, oh, those are the same thing. It's just that basically those processes are automatic internally. So pilots think that, hey, this is indicated. But we engineers need to realize that we already go through the process, indicated to calibrated, calibrated to equivalent. Then we are seeing equivalent airspeed. This is the equation of equivalent airspeed. And from pilot's perspective, this is essentially indicated airspeed, because this is what instrumentation indicates to you. Make sense? So don't be confused, because we use the terminology with two different meanings. Pilot says, oh, this is indicated airspeed because my airplane indicates this airspeed. Well, you should know this is actually equivalent, okay? Because the instrumentation is based on standard sea level density, equivalent airspeed, okay? So one thing remains after that, starting from either pilot's perspective, indicated airspeed, or our perspective, equivalent airspeed. The one last conversion process is from here to true airspeed. What do you need? The actual density is needed. In order to have actual density, you need two information. One is, of course, P infinity. This can be done by static port. You can sense the static pressure as you fly. The other one is, of course, OAT, temperature of your flight altitude. Okay? This may or may not be available depending on what you define the actual temperature when you're flying. Because think about that. Airplane is moving always, and then temperature may not be constant. You may fly through the hot zone, cold zone, hot zone, cold zone. Okay? And then how do you even measure it? Because you are moving. I want a static temperature. How do you measure that? You have to stop there. And then what is the temperature right now? That's what you want, right? How can you do such a thing? It's usually, physically speaking, it's impossible information. However, you can get fairly close value to it. It's called OAT. OAT may or may not be available, depending on the type of airplanes, type of flight, type of altitude, speed range. Anyways, I have a video. Okay. Try to understand what this pilot is saying. Okay. So having said that, let's hear what the pilot talks about. I have a video. Let's take a look.
To work out the true airspeed on a Puli CRP1 flight computer, just basically do what I do here. Say you have an indicated airspeed of 85 knots, and the outside air temperature is plus 15 degrees C at 5,000 feet, or whatever your desired altitude is. You just put the air temperature on the outside there, and the pressure altitude on the inside. You read off where your indicated airspeed is, so there was my 85, and I'll just read it on the next level up, and it shows me that the true airspeed will be 93 knots.
What is he talking about? Robert, are you okay? What is he talking about? Are you sleepy? Try to think about that. You're wasting time here. You can go home sleep if you want to. Then go ahead, answer my question. What is he talking about? What is it?
Talking about indicated airspeed.
What is indicated airspeed? And why does he need to do this?
Because
Why does he need OAT?
first of all, you found that the static temperature, and then I saw the values. I just didn't see what you did after.
I'm going to replay back to you once again. Answer my question, all right? Stay awake. All right? Robert?
Yes.
Okay.
To work out the true airspeed on a Puli CRP1 flight computer, just basically do what I do here. Say you have an indicated airspeed of 85 knots, and the outside air temperature is plus 15 degrees C at 5,000 feet, or whatever your desired altitude is. You just put the air temperature on the outside there, and the pressure altitude.
Pressure. What is pressure altitude? No. The pilot talks about pressure altitude. He's not talking about altitude. He's talking about pressure If the altitude is 5,000 feet, and if today is a standard day, this is the pressure. He's talking about pressure. It's not altitude. Altitude is estimate. If today is a standard day, we are probably flying 5,000 feet because airplane is sensing this much pressure. That's what he's talking about. So that means he knows the pressure, right?
Yes.
That's P infinity information he knows. That's why he's using this device. What else does he need?
OAT.
OAT. That's right. So OAT and then pressure altitude information gets you the real density of his flight, right? That is going to effectively convert from equivalent, which he's talking about indicated, to the true airspeed. If you're not nodding, you're not understanding. Let me play back once again. If you don't understand, ultimately, you don't have to take this class. It's a waste of time. Let's do it again.
To work out the true airspeed on a Puli CRP-1 flight computer, just basically do what I do here. So you have an indicated airspeed of 85 knots.
What is he talking about? This is what his airplane indicates. This is equivalent airspeed.
Yes.
Right, that's right. So this is E, knots in equivalent airspeed, okay? KEAS, that's right. And then he's writing the OAT.
Knots and the outside.
So OAT is given now. So he knows the temperature, OAT. The next thing is
Air temperature is plus 15 degrees C at 5,000 feet, or whatever your desired altitude is. You just put the air temperature on the outside there, and the pressure altitude on the inside.
pressure altitude he's talking about. Pressure altitude doesn't mean the altitude. He knows the pressure. If today is a standard day, this is equivalent to 5,000 feet pressure. So he knows the pressure value. Go ahead.
On a airplane, when they adjust the altimeter for the non-standard temperatures, does
You can do it, but let's not talk about those things. Again, it's always easier to make things more complicated. Let's just take care of this first.
You read off where your indicated airspeed is, so there was my 85, and I'll just read it on the next level up, and it shows me that the true airspeed will be 93 knots.
There we go. So this is the using flight computer to quickly convert equivalent airspeed, or from pilot's perspective, indicated airspeed, to the true airspeed. Very basic things. Now, as an engineer, we need to understand that kind of language, because we are the one designing airplanes. Okay. Now, obviously, airplanes, depending on the type, of course, you can adjust into non-standard values, but let's not talk about those complications. You can build only if you understand the basics. Then you can complicate it. You can apply those things later. We're not going to talk about it here. So that is the conversion process. Okay. That is the difference between those two equations. The only difference is the density ratio. Okay, so you come up with a density ratio to determine true airspeed. I hope I'm answering your questions there. Okay, so next page. Okay, let's take a look at example problem. Very simple example. The altimeter on a low-speed private aircraft is 3,000 feet. What do you mean by that, first of all? So your airplane is exactly flying 3,000 feet, is that correct? No. What do you know about altimeter reads 3,000 feet? Go ahead.
It's 3,000 feet based off your pressure.
Based off of your pressure measurement, airplanes essentially estimating you are probably flying 3,000 feet if today is a standard day.
Yes.
That's right. So you're actually given pressure here, not the altitude. That's what it means to have pressure altitude. Okay? So somebody please tell me the pressure value.
70,000 121 newtons per meter squared.
Wait, 3,000 feet. 3,000 feet standard pressure.
I'm sorry.
It's okay.
That'd be why it's long.
It's okay. It's okay to make a mistake as long as if you run it. So 3,000 feet standard pressure is P infinity. That's something airplane sensing. And then based on this value, your airplane is estimating you're probably flying 3,000 feet. That's what you call pressure altitude. what is the pressure then? How do you get that?
Sure.
Yeah, Chuds.
Okay.
Somebody please get it.
I got it right this time.
Okay.
1.8967 times 10 to the 3 pounds per square foot.
8967 times 10 to the 3
Yes.
pounds per feet square. PSF, standard unit. PSI, not the PSF. PSF standard unit. Correct. I think correct. Okay. So this is the actual measurement, not the 3,000 feet. You never know if you really 3,000 feet. Okay. But you know this is the pressure you are sensing. So you can use this value, of course, because this is measured value. You're able to measure this. The next thing is, okay, well, pirostatic tube measures a pressure of 53.3 pounds per square foot. What is it? What do you measure? Dylan, go ahead.
So that is the stagnation pressure,
No.
or the what is it?
That is P0 minus P infinity. This is Q.
Dynamic.
Dynamic pressure, yes, this is important. Okay. This is measured, which is 53.3 pounds per feet squared. This is again based off of fluid mechanics version of Bernoulli's equation based airspeed equation. So that's why I'm telling you, okay, go back to fluid mechanics, get the basics right. This is something you can determine using that device. This is a pressure difference between total pressure, which is center tube, stagnation point, to the static point, which is, this is atmospheric. Typically, I mean, this is zero gauge. Typically, like, if it's 3,000 feet, you're measuring this body, okay? So you can squeeze out dynamic pressure by using this device. That's the only information you can get, all right? So based off of those information, somebody please tell me density of sea level. This is the standard sea level density.
Another metric. That's not it.
Yeah.
0.0023.
0.0025?
Is it 2377?
Where did you get 25? No.
0.00.
Where did you get that by, Barbara? Where? Tell me. Where did you get that by?
Oh my God.
Eh? Where? I want to know. I mean, did you Google something or what?
I believe.
Okay. 1, 2, 3, 7, 6, 9. Where did you get this? By the way.
Okay, that's.
Where did you get this? This is a chart. Okay, good. So make sure you use the chart. Do you have a chart in your device? Because you have a device.
Yeah, I do have it.
You can access to the chart, right? Go ahead, check. Go ahead, access it. Take a look at it. Take a look at it now. Really, I mean it. Rather than sweeping. Take a look at it. Okay. I slowed down. I'm sorry about that. I don't want to hurt anybody, okay? So just stay back and relax and enjoy solving this problem, all right? So what's next? What's next? So out of those information, what kind of things we can get? Of course, equivalent, right? So equivalent is, okay, 2 times P0 minus P infinity. Of course, you know this is dynamic pressure divided by rho S. Go ahead, Michael.
So why did we even need to find T infinity if we were given the dynamic pressure?
That's right. That means you're saying this is going to be 2 times Q over rho S. That's what you wanted to say.
Yeah.
I agree.
Okay.
So let's use that. Great point. So this is 2 times 53.3 pound force per feet square, because this is standard unit. I just keep it as is. Density sea level 0.0023769 cubic foot. Okay. So if you compute, you're going to get equivalent airspeed. Please pick it up your calculator and finish up your computation.
211.77 feet squared, feet per second.
Okay, 211.77.
Yeah.
77?
Yeah.
Feet per
Feet
second.
per second.
And then usually this is converted into knots. You're not going to talk about it, but if you're dealing with knots, this is called knots equivalent airspeed. KEAS, if it's knots, okay? Because airplane pilots usually use knots. Now, we won't avoid it because we want to stay on the standard unit of airspeed. Now, if OAT is given, okay, OAT is independently measured. Usually, this is T infinity information. This is 50 degrees F, okay? This could be measured by instrumentation of your airplane, or could be measured by someone's, I don't know, weather balloon happen to be at that altitude. Okay, keep sending you, local info. I don't know. But anyways, I hope this is accurate, but this is outside air information, outside air temperature. And then, of course, T infinity, your airplane is capable to sense it. You know this value, right? Of course, this value. Yeah, of course. This is 1.8967 times 10 to the 3 pound per feet square. This is essentially static port sensing. Airplane has a static port. You can determine static pressure, which is atmospheric, of your local condition, local flight condition, your altitude. This is probably close to 3,000 feet. We never know. It's only estimated. Now, out of those, you can determine the real density of your flight condition, rho infinity, which is P infinity divided by R, T infinity, right? Mm-hmm. Okay, so let's just plug in. This is 1.8967 times 10 to the 3 PSF. This is standard unit. Gas constant is 1716. Pound, go ahead, question.
You had said that this is the actual density, but isn't this just the or estimated density because we don't know actual temperature?
That's right. So this is actually, you believe this is the real density, but we never know.
Okay.
That's one thing. Yeah.
Okay.
Yeah, that's a good point. Go ahead.
The 1.8967 times 10 to the third, the pressure infinity, does that say static pressure?
What do you think?
I think so.
Yeah, that's what it is. Okay. So if you compute this, the density you're going to get is 0.00216 726. Oh, that's a lot of digits. But size per cubic foot. This is the real flight density, at least you believe it is. Okay? Now, if this information is given, you can determine through airspeed, V infinity, which is, of course, now square root. Instead of using standard sea level value, you're going to use this value. That is flight computer that airplane pilot was using, right? So now this is 0.00216726 per cubic foot. And this is 221.78 feet per second. Okay? So this is, if this is in knots, this is to do. No, knots in to do airspeed, KTAS, if it's in knots, okay? Let's find out percent error between them. $221.78 minus 211.77 divided by 221.78 multiply by 100 gets you 4.5%. Oh, this is so small. But here's the important thing. Equivalent airspeed is always conservative estimate. It's always smallest value out of all of those ICET processes. So airplane pilots knows that your airplane keeps saying you're flying only 83 knots, but you don't believe it. So oftentimes pick up and calibrate, and oh, I'm actually flying 97 knots. That's what this pilot was talking about. Okay. Somebody was raising hand. I'm sorry.
Yeah.
Go ahead.
Is it necessary to calculate the Mach number?
What do you think?
Yeah.
What is the Mach number for this case?
So, it's,
Probably you don't care. This is low speed, less than 0.3. Density is constant. That's why you're using Bernoulli's equation, all right? Of course, you should be able to, I mean, you should check your Mach number, but the flight regime here is a low speed. Yeah, go ahead.
Yeah, I was gonna say using Bernoulli's equation because Mach less than 0.3, but it's still.
I'm saying the same thing. Yeah, right now. Yeah.
Yeah, you were answering my question.
Eh? Well, what is your question, by the way?
No, you were answering as a.
Okay, good. Go ahead.
So just like how we got a new equation for Bernoulli's, is there going to be a new equation for this greater than Mach, for numbers greater than Mach?
Ah. So that means, suppose if your airplane start flying more than 0.3 Mach number, what do you do? What do you do? You go like, oh my goodness.
You give up. You just give up.
Yeah, right.
No.
So what's next? You know, over the weekend, you probably start thinking about, oh, I'm doomed because now you're flying more than 0.3.
Oh my God. Oh, it's the running number.
What is the equation do you need to pick up? Okay. Well, I'm going to pick up Bernoulli anyways. Now we are going to pick up modified Bernoulli, which is compressible but isentropic, calorically perfect ideal gas. People call that energy equation, but it's Bernoulli's equation. A little bit more sophisticated, inclusive of first law of thermodynamics kind of more. So we can apply that equation for high speed, as long as you're not going to go beyond sonic, which is supersonic flight. Now, once the supersonic flight gets into play, your airplane is going to create shock wave, typically at the nose cone. And then you create the shock wave, something called a microcone. Your airplane's behind the microcone. As long as your airplane's behind the microcone, this area is actually subsonic speed, however, already compressed air. Density is higher, temperature is higher, pressure is higher. You're flying in a different condition. And then this shock wave formation creates another component of drag, something called wave drag. You have to add it, okay, to the all sorts of computation of your road speed, to the transonic, to the supersonic. So this equation covers up until sonic. Now, once you go to supersonic, of course, you have to wait until AE301 kicks into play. You have to solve for the formation of shock wave to begin, because that is going to drive lots of things. Then once you go beyond that, behind the shock wave, you can apply it, right? So that's how you do it in high speed. So this equation is going to be quite important. We're going to take a look at it on Monday. So starting point, we still have time today, huh? So starting point, where do you start? Let's get started on this. What is the starting point? What kind of equation do you want to pick up and apply? Eh? Oh, P plus 1/2 rho V squared is constant. No. This is Bernoulli. You can never do that to that. So you can basically say CPT plus V squared over 2 is constant. So instead, you're going to pick up this equation, right? So this equation can be more than 0.3 Mach number. Compressibility can be included. However, flow field still needs to be isentropic. So you cannot, of course, apply this equation across the shock wave. Now also, what is it? Calorically perfect ideal gas. You can actually apply it for a thermally perfect ideal gas, but in that case, CP is not a constant. You have to keep track of it, okay? Like I said, it's always easy to make things complicated. So let's just to take care of the easiest possible form to begin with. Then you can apply one thing at a time. 5 more minutes. Okay, so this is the condition, but Mach number more than 0.3 is okay. Okay, so this is the starting point. Starting from here, what are we going to do? We are going to apply this equation for the situation of pirostatic probe attached to the airplane. Okay, so this is pirostatic probe attached to the airplane. Now you're going to take a look at the streamline like this. Okay, then you have a side port here. You have a center tube here. You have a free stream here. Okay. So let's call this is infinity. This is 0. This is stagnation point. This is also infinity, isn't it? Because you're sensing static pressure. So right here is a free stream pressure, free stream temperature, and then this is your flight airspeed, density of free stream. Right here, velocity is 0, stagnation point. Pressure is P0, temperature is T0, density is rho 0. Those are called the total pressure, total density, total temperature. Those are the values measured at the stagnation point. Now, we are still assuming isentropic. That means flow speed is more than 0.3, pretty high speed. However, that speed is coming into stop right here isentropically. What do you mean by that? You're not going to lose any energy. So imagine that next time when you visit your flight line, okay? So the airplane comes home and touches down and stops. You just run into that airplane, touch the pirostatic. Do you think it's a room temperature?
No.
If not, it's not isentropic. Friction causes the heating, and that energy cannot be recycled. Can you scrape up all of those heats? Put it back in? No, you cannot do that. It's not reversible anymore, right? Friction causing heat, you lose that amount of energy. So in reality, this is not isentropic slowdown. So that's why in aerodynamics, we are going to differentiate between stagnation pressure to the total pressure. It's not the same thing. We assume that we can determine total pressure at the stagnation point. Is that really true? No. Only if it is isentropic. So question is, how much far away you are away from isentropic process? That is always the question. 0.3 Mach number is always the lower boundary. Okay. That's the boundary between high speed to low speed. Because that's where isentropic process, well, you know, can we still say isentropic process? Okay, really high speed airplane comes home from a mission, touchdown, and just run it and touch it. You're gonna burn your, oh my goodness, that's hot. This is not isentropic, of course. Okay, but next time, you know, those Cessna 172, you can probably still touch it. Oh, it's kind of hot, you know. But is it fairly isentropic? I guess we can say that. That's why we're using this equation.
Okay.
Okay. Right.
So are you saying like high speeds are isentropic?
High speed is not isentropic, of course. Do you think it's isentropic? You can touch like SR-71 right after Mach 3. Oh, you can cook something.
Yeah.
No. Lots of friction heat. Okay, anything else? Go ahead.
I just wanted to point out that you said you can only assume that the total pressure is at the stagnation point at low speed.
If it is isentropic.
If it's isentropic, but when it's high speed. Because
you're going to lose lots of energy by slowing down to 0. Okay. If this is really high speed, slowing down to 0 requires lots of non-reversible process friction. Causes lots of heat. Yeah. Anything else? Let's stop here today. Okay. As we come back on Monday, we're going to continue the discussion of this airspeed limit. High speed, more than 0.3. Have a great weekend.
You too.
Get out of here.